all this on piezo. Great. So in the last lecture, we went into the details of Neyman-Pearson detection. We looked at the contrast between Bayesian detection and Neyman-Pearson detection, right? And depending on how you formulate the problem, right, whether you need randomization or not changes. So that was a main takeaway. Let's do a brief recap of that, and then we can go to the sequential detection. That's the focus of today's class. So again, like I always start with the likelihood ratio detector, right? So if we have two hypotheses, this likelihood ratio is the minimal sufficient statistic, and hence any detection problem you would consider would be only based on that, which is a nice thing, right? So, and this likelihood ratio detector, what we said is a threshold detector. So you want to say that if it's beyond a threshold, you declare your decision to be the theta 1 or alternate hypothesis when it comes to Neyman-Pearson detection. And the whole methodology was in terms of designing this threshold, right? So we saw in the Bayesian setup, the threshold depended on the priors. So it's essentially the ratio of the priors, and if you have more variance in your data, you would rely on the priors, right? So that trade-off we could see in the design of this threshold. We looked at that problem of Gaussian setup where it was more clear, like the trade-off between variance and the prior. Right, so when there's more variance on your data, you rely on the prior and vice versa. So that was a nice aspect of the Bayesian setup we saw. And the other one was that deterministic detector is optimal, right? You don't need randomization. And that came from linear programming, because in the Bayesian setup, you can frame the problem of risk minimization in terms of minimizing a linear combination of costs across the different hypotheses. And the constraint is your decision variable should be in the probability simplex, right? Because naturally it's a distribution, you cannot violate that constraint. And so we know in the case of linear program on a simplex, we know the optimal solution is one of the vertices, and the vertex means there's no randomization. Right, so that was the takeaway from the Bayesian setup. Right, so the main two takeaways to summarize, the first one was that the trade-off between prior versus the data, right? And this, by the way, is going to be true even in more complicated scenarios, right? So in general, if you have prior information about your data and noisy data, how do you balance the two is one of the core problems in machine learning. But in this simple setup, we could see that trade-off explicitly. And the second one was no randomization is needed, because it's a linear program. Right, so these were the two main takeaways for me. Anything else we can recall from the Bayesian setup? Right, these were the main ones. And then we went to Neyman-Pearson. And here, the philosophy is that the alternate hypothesis is the one that could be a problematic event. There could be costs involved, human lives at stake involved, and so you want to be able to detect it as much as possible. But on the other hand, if you make a lot of false alarms, right, people will no longer trust the system, or their costs for false alarms. So you don't want many false alarms, but the focus is on detection, and that's where it was this trade-off between the two types of errors, and we also call this the region of operating ROC curve, right? So let me just say ROC. So it was the ROC curve where you have the trade-off between false alarm versus detection probability. And so here the idea is if you have a constraint on your false alarm, right, what is the detection probability? And so, you know, this line of x equals y is the trivial detector, right? So if you just randomize with this much probability for the null hypothesis, you get the straight line. So, and that's why the ROC curve is always concave. It's above that x equals y line. So that was the first thing we noted. And so higher the curve, the better, right? So if there is one detector that's strictly above the other, that detector is preferred, right? So that was the idea with this trade-off. You can think of it in terms of this ROC curve. And the second one was the notion of uniformly most powerful detector, right, or UMP. And the idea is, you know, is there a detector that's uniformly better than everything else? So its curved line is strictly above all the other detectors for any given choice of false alarm, meaning, you know, uniformly across all choices of false alarm as well as the model parameters. So that was the notion of uniformly most powerful, and what we saw was this likelihood ratio detector is uniformly most powerful, but it was only under deterministic detectors, right? So, and if you recall, the derivation involved integrating over the regions where the detector makes the decision to be the alternate hypothesis. So that was critical, but then we saw this example of biased coin where randomization helps, right? That was the third important point, that right, you can do better with randomization. And the intuition here was if the likelihood ratio is not absolutely continuous, so it has jumps, there's an atomic measure involved. So let's say it is something like so if there are discrete jumps in the likelihood ratio detector, you can't incorporate all values of the false alarm, right? Because false alarm is given by the designer, and if you can't satisfy that level of false alarm, you can't get the optimal detector. So, and so the slack between the, you know, jump is where randomization helps, right? So, and that's what we saw was a way to get towards optimality. Any questions so far here? Right, these are the main takeaways. Okay, and so the next aspect which we started discussing was now doing sequential detection. So the example I gave in the last class was, right, so let's say this problem that I have two Gaussian distributions. Let's do this again. So I have Gaussian distribution at a certain mean, let's call it theta naught, and then another Gaussian distribution at another location, let's call it theta 1, right? So let's say this is 0, this is 1. And so the idea was, you know, if I have a fixed sample size, in order to get a certain level of errors, right, I can go back and compute what that size should be. For instance, I can write down my likelihood ratio, I can write down the errors for what that likelihood ratio detector would do, right? Both in Bayesian or frequentist setup, so I can do that. But what if I got lucky? Suppose my sample that I saw was saying it's 3, right? So if I know from like the Gaussian distribution, right, that seeing 3 under the null hypothesis or under theta naught is extremely unlikely compared to theta 1, right? So I know this likelihood ratio will be high when I see 3. So in that case, suppose that I'm satisfied according to my error constraints that it is theta 1, I should just go ahead and declare. And that's what sequential detection is about, right? So online you make the choice whether you're satisfied in terms of the data you've seen. When I say satisfied, I mean you have certain constraints on what the error probability should be. And if you're confident that those constraints are met, you can terminate the problem. Right, you can make the decision. Otherwise, you keep collecting more data. And this is critical for many domains, right? Because data is the new oil is a term I hear. I don't know if that's how I want to frame it, but indeed data is very expensive, right? So, the sequential detection is a foundation for active learning and online learning, all these other paradigms, right? So this is the foundation. So if you can get away with less data, you should, right? And that's what we are building here. So have any of you used any form of active learning, sequential decision making? You've either done as research or used it in any practical setting? Did someone intern at Facebook here? Was that you? Yeah. Were you doing any recommendations?
Yes. However, we didn't really have a choice of kind of setting how much examples we want labeled, because the labels just come from users clicking. But I mean, there's the subtle active learning problem, which is how much of our testing group do we want to give away to each experiment? So if I'm going to use 6% of the population, I should better be convinced that my experiment is worth doing.
Right. So it's more kind of higher order, notion, right? So still data is valuable even in a place like Facebook, because there's only, what experiments you launch, there's only finite number of them you can do. And the other is, right, the effect it has on the population. You do a weird experiment, people are like, okay, what happened to my interface? Why is it behaving this way, right? Or why is it showing me these news articles? So you want to also be careful about that. So it's not just the question of data being expensive, but it's more complicated because it's non-stationary, right? So in this case, the data distribution is not changing, right? So I can keep collecting samples. I'm assuming, right, my hypothesis distributions, they are the same, right? Both, my model is not changing, but that's not true in real world, right? So as you start to change your experiments, first of all, it's not just a simple rule of whether I should collect more data or not, but what kind of questions to ask, what kinds of tests to do, right? And then as you're doing it, right, the environment itself keeps changing. And that's why it's much more complicated. So we won't be dealing with that here today, but you can see that, right, this is probably the simplest possible setup for sequential decision making. So we are assuming there are two fixed distributions. You're getting IID data from that, and you want to decide between whether it's, right, the first distribution or the second. You're given those two fixed distributions. Right? And you want to do it in the quickest possible time. Okay, so that's the setup. And so as we said, to has formally set up this problem, there were two main ingredients, right? So one was the stopping rule. So if I'm going to design this sequential detector, right, it should have the stopping rule and then it should have the terminal decision. Right, so the stopping rule, what does it do? It takes all the data up till this point to decide, should I collect more or should I stop? And once you stop, you make the terminal decision. And the terminal decision is same as before, right? Which of the two hypotheses is this? And what you're given are the error constraints. Right, so we'll use the same notation as in Neyman-Pearson, but this is not Neyman-Pearson, right? So we'll use the notation alpha was the false alarm. So alpha was probability, right? So you assume that the data is from theta naught, but you make the decision to be 1. So that was alpha, beta is the power, right? So where it is indeed theta 1 and you're making the decision to be theta 1. So we are given these constraints, right? So I tell you before you start collecting data, let's say I want 90% power, right, or 90% detection probability and say 30% false alarm, right? So I tell you these constraints and then it's up to you to collect as little data as possible and satisfy those constraints. Okay, so that's the setup. Any questions here? So what do you think will be the form of optimal detector for this? Okay, so for that, optimality, right? So how do I define optimality in this setup? What would be the criterion? Intuitively, what should optimality be about in the sequential setting? I mentioned it multiple times.
Given that you satisfy your
Right.
data levels, that you collect as little data as possible.
Right. So how do I mathematically frame that? So the amount of data, what is it? It's a random variable, right? So when it's a random variable, as little as possible, how do I frame that? How do I compare two random variables?
You can compare their mean or something.
Right, so the mean is the simplest, right? So if, I guess if you take an advanced operations research class, for instance, this whole area of stochastic orders, right? So the question of how to compare a set of random variables is non-trivial, right? Because if they're coming from different distributions, right, you can't compare apples to apples. So a simple way is to say, all I care about is the mean. Right? I mean, sometimes you know it's more than the mean, but at least we can start there again. So again, the mean under what? Right? So there is two distributions, right? There's mean under theta naught and mean under theta 1, right? So because either of them could occur, right? So that's why you want to look at the mean of this, the number of samples collected under both the distributions, and ideally you want both of them to be as small as possible. Right, so that's the minimization problem. Okay, so is that clear? So, okay, so we can frame optimality. Of course, this n depends on let's say, a detector delta, right, to be complete, and then I minimize over delta. So ideally, I want the same detector minimizing both, right? So meaning for a given detector, I would have both these expectations, and I wanted the optimal detector to be good under both these expectations compared to any others, given these error constraints. Is that clear?
So why are the constraints equalities?
Oh, this one, oh, I just defined it this way, right? So, yes, I mean, as a constraint, it would be inequality, right? So, but then you expect that the optimality would be met at the boundary, right? Because you want to kind of, right, it wouldn't be in the interior of this set. I mean, I just defined this one right now as this, but if you want it to be in terms of the detector, let's say, alpha is the given constraint, you want your right error to be less than alpha, and you want your right detection probability of the detector to be bigger than beta, right? Yeah, so that's the more careful way of putting that. But is the optimality criterion now clear? So what do you think is the form for the optimal detector, optimal sequential detector? What have we seen all along? All along, all the optimal detectors have the same form. Right, so what form is that?
A likelihood ratio?
Right. Right, so that's how we had it so far. So, right, so we do think it should be likelihood ratio, right? So let's say, you know, I have this likelihood ratio detector, and now I have different trials, right? So, of course, if I have multiple IID samples, I would be taking product along the way, right? Because, you know, with one sample, I have likelihood ratio of that sample, but the next one I would kind of multiply. So let's say it's the product up to this time n, right? So maybe I'll right? So if my y is my vector of samples, and they're all IID, right? So I have this likelihood ratio that I have accumulated until now. So what should I be doing? Let's say, you know, the likelihood ratio in the first sample was here. After 2 samples, it went somewhere here. Let's say after 3 samples, you have here. After, say, 4 samples, it's somewhere here, right? So I keep, you know, I can keep looking at how the likelihood ratio evolves as I have more samples. How do you think I should make the decision? Right, the very first decision is, of course, when to stop or not. How should I design that? What does your intuition say?
You want to have a higher threshold, you have less data.
So you have less data, you have higher thresholds. So to do what? I mean, first of all, I want to decide whether to stop or not, right? So deciding what the actual hypothesis is only comes later. So my first stage of decision is, should I continue or not? How do you think I'll come up with that decision? Does that make sense?
Yeah, I thought that maybe, yeah.
Is that what you were getting at? Sorry, I couldn't.
Yeah, I guess maybe I'm not speaking clearly, but I was imagining if you want to have the threshold to stop should be higher if you have less data. So you either want to stop if you have an enormous, I guess, yeah, you want to have a minimized amount of data. So
Right.
it's a function of both parameters, but maybe I would be more specific to say.
Right, so it should depend on these error constraints, of course. Right, so because your threshold is determined by how much error are you demanding. If you have very weak constraint, you should stop earlier. Right, so how do I see that reflected in this likelihood ratio? Is that helpful?
I have a question. So I just want to make sure I understand that you fix both beta and alpha. It's
Yes,
not like,
yes. Unlike the Neiman-Pearson where we fix alpha, we optimize for beta, right? Here you fix both alpha and beta and you optimize for the number of samples, expected number of
now there's
samples.
a problem. It might be the case that with your alpha and beta, there is no even anything that can satisfy. Right? I mean,
Then you can just keep collecting more and more data, right? With infinite amount of data, you can satisfy any alpha and beta.
I see.
It's IID samples, right? So it's, if it is not IID, I agree, right? You don't know. But if it's IID samples, asymptotically, you would make a perfect decision because you know everything about the distribution, right? That's what makes
There is
this,
no maximization for alpha beta as long as we satisfy them.
yeah, right? That's what they are given. Right? Is that clear to everybody? Neiman-Pearson, alpha is given, but beta is optimized. And the number of samples is fixed, right? Whereas here, both alpha and beta are fixed, and number of samples is a random variable. So yeah, how do you think I should design my stopping rule?
You're going to have an upper threshold and a lower threshold, where if your likelihood ratio is between that, you're going to keep collecting data, but whenever you get above or below that, you'll stop.
And the intuition for that's right? So what is the intuition? I guess, the intuition we had earlier was if the likelihood ratio is above a certain threshold, it should be the alternate hypothesis, right, or theta 1. And the intuition for that is, that threshold would depend on this alpha beta parameters. And indeed, it's the opposite is also true, right? So there is nothing special about theta naught versus theta 1 here. You can do the argument even the other way, so there should also be a lower threshold. So the intuition is if your likelihood ratio is very high or very low, then you're certain, right, of which hypothesis it is. On the other hand, if it's in the middle, that's when you don't. Right, so if the likelihood ratio is, say, like nearly 1, you have no idea, right? Both are likely. Whereas if this is 1,000 or if it is 1/1,000, right, then you're quite sure about what the hypothesis is. And so that's why we have now these two thresholds. We call it A and B. And naturally, they depend on alpha and beta. Is that clear? I guess, let me see in the notes, probably the lower one, I've put I'll use the convention in the notes. Yeah, makes sense because, so if I make, let's say, beta to be very large, what happens to B? If I set beta to be nearly 1, what happens to B? Beta means the power, right? So I'm asking that I should be able to detect this alternate hypothesis whenever it occurs. So if I demand a high beta, what happens to B? Yeah, it should go further up, right? Because you intuitively would need more data to satisfy a larger beta, right? Because beta is the good thing, it's the power, right? So it's about not, it's about being accurate under the alternate hypothesis. Is that clear? So if I set a large beta, right? So if I set beta to be nearly 1, B should almost go to infinity, right? Because you never stop, you keep collecting data to satisfy a very large required value of beta. Is that clear? Questions? Yeah.
Beta is just the probability that you say it's hypothesis 1 when it's actually hypothesis 1?
Yes, it's...
If your B is all the way at the bottom and you always say it's hypothesis 1, won't you also satisfy that?
No, but this is the threshold, right? So I mean, like this is the threshold of stopping. So the intuition is if you're asking for a higher beta, you would need more data. Right, so I mean, it's also like, you would also have, of course, have to push A, right? So A is the lower threshold, so I'm only looking at the upper threshold at the moment. So you can't, so if you just kind of bring this down, that means, right, it will satisfy this threshold much earlier with fewer samples. Right, that's not what would happen, right? If you ask for a higher beta, you would require more samples to satisfy it. And that's why the threshold moves further up. And similarly, it's true for A, right? So if you want to look at the trade-off between alpha and A, there is a similar intuition you can have. So just the intuitions, right? So depending on how you set alpha and beta, right, how many samples you require will change. But that's much easier to see in terms of A and B. If this region between A and B is smaller, right, you stop earlier, you need fewer number of samples. If that region is wide, you need to go on for further, like longer time. Okay? So how to analyze this, I guess, is is a challenge, right? So I mean, the analysis will be more challenging compared to the fixed sample case, precisely because even the number of samples is a random variable, right? Like so far, when we think of, say, law of large numbers, or right, like all these identities we have with sum of random variables, it's usually on a fixed number of random variables, right? Not on a random number. But this is where I think it's called the waltz theorem. That's, I think, useful. What is it called? Let me just, yeah, the waltz equation. So this is useful. And this is general. I think this is from the 1950s or even earlier. So what this says is, right, like now what I want is sum of random variables. Let me just say arbitrary, but IID distributed random variables. But here even n is a random variable, right? And what I would like is expectation of this sum. Right, so how do I analyze this? If n was fixed, then I know, right? I can just linearity, I can take the expectation, everything's fine. But now what do I do when n is also random, right? So you have to be careful about this. And why do we need this? Because we can set the zi to be the log likelihood of each sample, right? So it's the product of the likelihood ratios. If you take the log, it's the sum. Right, so we'll need it to analyze this likelihood ratio detector, but first we have to grapple with what this is.
So you assume that N and Z are independent or independent?
It's not, right? So in this case, it's not, right?
Yeah.
So the idea is, in the likelihood ratio detector, all the samples of likelihood you've collected so far, you determine your N based on that, right? So the minute you stop, right, there's no dependence on the future, but it is dependent on all the past, right? And that's what makes it even harder. This N is not independent of ZIs. If it's independent, right, then you could argue that, right, I can decouple the two. But then if it's dependent, how do I do this? Surprisingly, under a very general case, right, it is still equal to the expectation of the N times the expectation of Z, right? So they're all IID distributed, so you would be the expectation of Z. But yes, if it was independent, this is more believable, right? You would have expectation of N times expectation of Z, but you don't need complete independence. And I think the most general setting here
But you assume that
it's a stopping time, so, right? That's all you assume, that N is a stopping rule. So this is true for any stopping rule, right? So stopping rule means, right, like you observe all the ZIs, right, up till that point to decide whether to proceed or not, which is exactly what we're doing here. I mean, it's quite surprising, at least to me, right, when I first saw it, because when this N is completely dependent on these ZIs, right, and this is still true. But I think it's a very nice result. And yeah, so for this, right, this is, so I think how this goes is you can write down the sum of ZIs to N in terms of, I think like a fixed, you'd slightly rewrite this, right, in terms of the, you just write it in, you want to remove N from the summation, right, because that's, otherwise you can't handle this. So instead what you do is you just send this to infinity, right, but you can now condition on an event, or rather you look at an indicator function that, right, N is, so you will only use I, right, a certain sample only if N is bigger than I, right, bigger or equal to I. So do you agree with this identity? Right, that's the definition of a stopping rule, right? Otherwise you don't end up using a sample if N is above that. Sorry, N is below that, the other way. Is this clear to everyone? Because this is the critical piece. Yeah, so now let me fix I. So this random variable Zi and the random variable, the indicator event, right? So this is an event. So of N being right, greater or equal to I, are these two dependent or are they independent?
So you assume that this is a stopping time.
Yeah.
Stopping.
Yeah.
So it's by definition. Okay. So by definition, I guess they're independent.
Right. Is that clear to everyone? Right, because it's a stopping rule, these two are independent. So I'll use this notation, by the way, for independence. Right, because it's a stopping rule.
Can you say a little bit more why?
So because it's a stopping rule, right? So the event of what happens to n beyond this point, right, is independent of Zi.
Because you've already stopped. So
Yeah, exactly. Right, so now it's not so surprising. If they're independent, you can now take the expectation, right, of both the terms separately. So I can take here expectation. I take the expectation inside because of linearity, because of independence. I can take the two expectations here. So now if I take this summation inside, what is this identity? What is this? I mean, you already know, right? I've written the formula above. What is it? It's expectation of n, right? And if you recall expectation of a discrete random variable, right? This is an identity we use. Discrete non-negative random variable.
Ask you something. At any point did you assume that this stopping rule stop almost every, or it should stop at some point, right? You assume that.
No, it could go up to infinity, right? Of course, then if you did, yeah. So, I mean, of course, on both sides it'll be infinite, right? That's okay. Right, so this is an identity you may recall from probability. Any questions here? Okay, so this is good to know, right, in general, if you're doing any kind of stopping rule, right, how does the random variable of, that corresponds to the stopping time depends on the samples collected, but still you can use the waltz rule and think about the expected time of stopping in a simple identity. Okay, any questions here? Yeah? So we'll apply it by, as I said, by having Zi to be the log likelihood, right? Because now that's a summation. And so if I use this waltz rule here and I look at the expectation under each of the hypotheses, right? Let's say theta I, I'll use for, the ith hypothesis, right? So the expectation of n times the expectation of C, right? So that is log of the likelihood. Right, so this is the expected log likelihood, at the time of stopping, right? So this is what I want this to be. And so if it is, say, under theta naught, I want that to be equal to log of A, right? So I'm just like turning all this, by the way, this rule is called sequential probability ratio test. Right, using these two thresholds. Sorry, I missed that earlier. So I have this SPRT with thresholds A and B. But if I now convert all that in under the log transformation, right, it would be just now log A and log B. And now, right, I have like kind of again these two thresholds. Okay, and my distribution is now the log likelihood over my set of samples. Yeah, so if I now use the waltz equation, I can look at, right, what happens to the accumulated log likelihood at the time of stopping. Right, so under null hypothesis, you want it to hit this lower threshold, right, and that's why that should be equal to log A, right, so right, so you would have like log A under the null hypothesis, right, but the null hypothesis occurs, right, with probability 1 minus alpha, right? So meaning in that, sorry, under that probability you would be choosing the null hypothesis. And then for the other side you have otherwise, or you could be hitting the other threshold, which is log B, and in that case, right, you would be right, so you would be, paying for the false alarm, and then that is alpha. Yes. So I think, it took a minute to make sure, but do you see this now? Right, so because the stopping rule is you either hit log A or log B, right? Those are the two possibilities. And I'm looking at the expectation under theta naught, right? So in this case, if I hit log A, then I'm correct, right? Because the underlying hypothesis is theta naught, and I'm hitting that, I'm hitting log A, so I'm declaring it's theta naught. And that happens with probability 1 minus alpha, right? And with probability alpha, I make the false alarm, and that's when I hit log B, right, the upper threshold. Is this clear? So what can I do a similar identity under theta 1? So what would this be equal to? So if I hit log A, right, what is the error, what is the weighting I should use?
1 minus beta.
1 minus beta, right, because that is the misdetection. And then if I hit log B, it is beta, right? So now you can see that how A and B are connected with alpha and beta, right? So this identity makes it possible to write down. Okay, so all we did here was use the waltz rule. Of course, this this expectation should also have theta naught and theta 1, right? Sorry, because so with this, I can come up with now what is the expected number of samples I need, right, for a given alpha and beta and for a chosen A and B. Right? So I can come up with this before I even collect samples. I can come up with an estimate of what is the expected number of samples. That's what this equation gives me. Is this clear? So what we did was we had the waltz equation, and with that we could evaluate what is the expected number of samples I would need under each hypothesis, right, for a given alpha and beta and for a chosen set of thresholds. Okay? Yeah, so now, right, so this is the sequential probability ratio test, the Wald and Wolfowitz theorem. So the Wald-Wolfowitz theorem says that this is the best you can do, Wolfowitz. So what it says is this is the best you can do, right? So intuitively, I think we had already convinced ourselves this is the best we can do, but that's what the Wald-Wolfowitz theorem says. So meaning if I'm giving you a certain alpha and beta constraints, right, the optimal sequential test that minimizes the expected number of samples under both the null and alternate hypothesis, or under theta naught and theta 1, is of the form of this ratio test. So you have this upper and lower thresholds, and then you test this likelihood ratio sequentially, right? So of course there is some choice of A and B, right? So we didn't fully specify how to choose it, but you can see that it would be, monotonically dependent based on alpha and beta. So that's the theorem of optimality. I won't go through the complete proof, but I'll give you some intuitions of why this is true using an auxiliary Bayesian problem. So, so far, by the way, this is all frequentist, right? So there are no priors I've set up, and I've set for any choice of theta naught and theta 1, right? So there is, this is frequentist problem. But there is a nice connection between this frequentist sequential problem and the Bayesian problem. So can you think of costs that I can design under the Bayesian setup that would mimic this notion that each data point is expensive, right? So can I, now I'm switching to the Bayesian setup. Right, so if it's Bayesian, I have say my prior distribution, right? So my prior distribution tells me what is the probability of, I think let me use the convention here, of theta naught. Okay, so I'm going to choose the same theta naught and theta 1 as the frequentist problem. And then I want to set up a Bayesian problem that mimics the same flavor. Right? So my goal is to ultimately come up with, right, a similar sequential probability ratio test, which is also optimal for these Bayesian costs. So if you recall, in the Bayesian setup, we had the cost, right? We had the cost minimization. If you recall, we had the cost of making a certain decision under, right, certain underlying hypothesis. So we have the freedom to design different costs. So how do you think I should design the costs to mimic the sequential nature? I can put a cost for collecting samples, right? So just the fact that I collect the sample is, say, some cost. And that cost, I'm going to call it as C, right? And so let me look at the expected cost. Yeah, so if you recall, the risk was the expected cost under each hypothesis. But let me first define the cost, right? So let me say under theta naught, right? So if I have the decision variable, but also I have the now stopping rule, right? So it's a combination of both. Let me just directly write down the risk. I think that's easier. So if you recall the risk under the Bayesian detector, it depends on the prior and it depends on the detector, right? So what I'm going to do is, let's say with probability pi, the underlying hypothesis is theta naught, so that's the probability, and if I now make the decision to be give me a second here. Right, so there is now, so under this, the running cost is C times the expected number of samples under the null hypothesis. And then there's a terminal cost for making the decision, right? And the terminal cost, I can set it as making the error, and I would be making the error if I, say, chose it to be theta 1 instead of theta naught. And I will put that cost to be W naught. So this is the cost of false alarm. Right, and this is the cost of sample. And then the other possibility is when I have the underlying hypothesis to be theta 1, right? So in that case, I can make an error of choosing the terminal decision to be theta naught. That happens with probability 1 minus beta. And then the cost I pay, I'll set it to be some W1. This is some fixed number. And again, there's a running cost for the samples. Okay, so I mean, it feels a bit unnatural in the beginning, but I hope now it's clear, right? So this is my choice, right? So I've set up now a different Bayesian problem that I'm trying to connect it to this frequentist problem. So far, I haven't made the connection explicit, but my goal is ultimately, right, that there should be one-to-one mapping between the Bayesian problem and the frequentist problem. And so that's why I'm trying to use as many parameters of this frequentist problem to also design my Bayesian costs. Okay, so intuitively what this Bayesian problem is telling me is, right, there is cost of collecting samples. So each sample costs you some value C, and the expected number of samples, right, under each hypothesis, I have some expectation here. Right? So that's the total cost of data collection here. And then there is a cost of making errors. Right? And I'm looking at the two possibilities. With probability pi, it'll be theta naught. With probability 1 minus pi, it'll be theta 1. Okay? And I'm just setting some cost. There's a cost of making the false alarm. There's a cost of making the misdetection, which is W naught and W1. Is this clear? So if it's a Bayesian problem, I can ask about minimizing this Bayesian risk, right? So the detector that minimizes the Bayesian risk is the optimal one, and we'll use this notation V of pi for the minimum Bayesian risk. But before we plot the minimum Bayesian risk, so let's have some intuitions. So let's say this is the pi, right? And then I have the Bayesian risk. Okay, let me just first kind of make some observations here. So the Bayesian risk will be something of this form. So let me first draw this, and I'll say in a minute what it is. So this is the line. So let's just look at this line, right, W naught pi. When do you think I'll, achieve that line? So what kind of detector achieves the Bayesian risk equal to W naught pi? Right, so this is the Bayesian risk, and now depending on the false alarm and misdetection of this detector, that's what this ends up being. So is there a detector that achieves risk equals to this, this line? How do I achieve this value? Can I think of a simple detector that does this?
You always guess theta 1.
Exactly, right? So the detector is always having the output to be theta 1. Is that clear? Because if the detector is always saying theta 1, the false alarm is 1, right? And this will also vanish. So and then C is 0 because you're not even collecting samples. You have 0 samples. You just say theta 1. Okay, and similarly vice versa for the other line. Right. So those two lines are always achievable. So your detector should be doing something more intelligent than that. Right. And so let's say the optimal detector, that achieves this minimum risk V of pi has this concave shape, and let's say it intersects with the lines in this way. Right. So let's say there's two values of priors. I call it pi L and pi U. Intuitively, what does it tell me? So below pi L, which one is higher and which one is lower? This one is lower, right? And above pi U, this line is lower. So what this tells you is, right, so there is a regime where you shouldn't be collecting any samples, you just go by priors. So the intuition is if the prior is too low or too high, right, there's no need for data. And this kind of goes back to what we were seeing in the Bayesian setup too, right? If you can trust your priors, you have a lot of information in priors versus the data, right? You don't, in this extreme case, you don't need to collect any data. And so the idea is only in this middle regime is where you would need to collect the data. So the idea is there's kind of like, the best detector would collect, say, no data in some regime, right, collect data here in this middle regime and again collect no data. Right, so that's how the optimal detector would look like for this Bayesian problem. Is that clear? Right, the intuition is if your prior is too low or too high, right, I'm better off not collecting any samples. And of course, that depends on my cost of samples, right? So there is this pi L and pi U is a function of C because it also depends on what is the cost of my samples and what is the cost of my errors. There is the trade-off. We haven't made that explicit, but intuitively you can see that though there'll be a trade-off between these quantities. And based on that trade-off, right, there is only like an intermediate regime of my priors where I would be collecting samples. Otherwise, I would just go by my priors. Is that clear? Right, because if I didn't collect any data, I would get these straight lines. So my optimal detector, right, should be just using that, right? I shouldn't be collecting data. But there can be like an intermediate regime where data collection is useful. Okay, so those are some intuitions when I set up the Bayesian problem in this form. And what the result says, which I won't be proving here, is that there is a one-to-one rule, one-to-one mapping. So if I tell you this is the frequentist problem with these parameters, I can map it to a Bayesian problem. Right? Some quantities alpha and beta directly map here, right? But then the C and pi will be a function of A and B here. Okay, and so vice versa, right? So if I have a Bayesian problem, I can map it to a frequentist problem. So there is a one-to-one mapping. And what this helps us kind of also intuitively see is, right, you can frame the problem of minimizing the number of samples in terms of having an auxiliary cost in the Bayesian setup for collecting samples, right? So in many ways, the Bayesian problem can be easier to handle because, right, this is overall like now it's the expectation over also theta 1. It's an expectation over theta, right? So you have this Bayesian risk, and it's easy to think about minimization. So this is more convenient, but the main message is you can view the sequential problem both from the Bayesian lens as well as the frequentist lens.
I was just wondering, in the Bayesian problem, it seems like there's like 3 more variables, like W0, W1, and C, that the frequentist setup doesn't have. So are those like, is that something you can determine?
No, and that's what I said is it may not be that easy to map, right? But there is an equivalent mapping. So the idea is every problem here can be mapped to a problem here and vice versa. Finding that mapping may not be as straightforward. But I think there is constructive one. Yes. So in one case, I think it's easier than the other. Right. So I didn't give the exact expression, but yeah, it's possible to kind of write one in terms of the other. But intuitively, you can see why, right? Because if you set up a Bayesian cost of this form, right? There is now a regime of priors where you collect samples and you aim for minimizing the collection of samples. But you trade that off with your false alarm and misdetection constraints, right? So that trade-off you can see between the two costs here. And right, similarly, if I set up the cost this way, I can always turn it back into a sequential probability ratio test. Okay, so I want to see that intuitively. I mean, there is like certain amount of math that will get you the mapping, but I want to mainly cover the intuitions here. Any questions here? And using this mapping, you can prove the Wolfowitz theorem, arguing that this SPRT is the optimal one, because we can go through the Bayesian route, and if you minimize the Bayesian risk, we know it's optimal, right? And then there is this one-to-one mapping. So that's what, right, intuitively gives us the proof of optimality. Okay, so what are the main takeaways with this SPRT or sequential probability ratio test, right? The main one is if you are now given the freedom to stop whenever you want to design both lower and upper thresholds, right, to satisfy the error constraints, right? So here you're given the error constraints and you have the flexibility of collecting samples. And you do that by designing thresholds on both the ends. And then we looked at the waltz equation where it's a nice property of the stopping rule that you can have the same identity as in this set of, sum of fixed number of random variables, right? You have the similar identity as in that case, and we can use it to evaluate what would be the expected number of samples you would collect under each hypothesis under given thresholds. So that's what we saw here. And then in the last part, I gave you some intuitions on how you can convert this frequentist problem also into an equivalent Bayesian problem where you're looking at both the cost of collecting samples as well as the terminal cost of making the decision, right? So once you also have a prior, you can look at the Bayesian risk. Okay, so that's the overall kind of takeaway for sequential detection. Any questions? Is that clear? Yeah? So in next class, I'll be now switching to estimation, right? So far what we did was binary hypothesis testing. I think in a few places I commented how to extend it to Emery hypothesis, and you can see it already gets quite complicated, especially the Neiman-Pearson setup with more hypotheses is quite complicated. The sequential test with more hypotheses would also be not as straightforward, right? But on the other side, the estimation is one to do with now, right, like kind of an arbitrary domain of parameters, and mostly we'll be thinking of continuous domain, but in many of them will be special cases will be the detection, right? Because when it's just two hypotheses, it's two possible values of theta, it's much easier to come up with these decision rules. But what if it's now a continuous domain of theta? How do you come up with optimality, right? Because many things we discussed here is quite, right, like kind of designed for finite or even sometimes binary hypothesis. So we can't easily extend these notions to the general estimation problem. So we want to ask, what is the notion of optimality? So the main ones we'll look in the next class will be minimum mean square error, right? So the idea is you now have an estimator for theta, and for any choice of theta, right, you want to make sure that you minimize the square error, right? So that's a common metric. Again, there are pros and cons to it. I'll, I think, also give you some other possible measures we can use, but the mean square error is the most common one. And when it comes to mean square error, we'll look at the decomposition, we'll talk about bias, we'll talk about variance, and then we'll ask, can we think about uniformly minimum variance or minimum mean square estimators, right? So if you recall, in Neiman-Pearson, we had the uniformly most powerful one. For any choice of underlying parameter, can we have the best one? Is that possible to carry over to estimation, or is it not, right? So we'll look at, what are the things we can extend and what are the ones that get much harder with estimation. Okay, so that'll be next class. Great. Thank you.